My name is Ritesh, and today I will be discussing whether a quantum random walk model can effectively describe reasoning response time dataset. In cognitive decision making research, understanding the underlying cognitive process has been of great interest. Response times has been widely evaluated to interpret mechanisms of cognitive processes in fast decision trials. For slow decision trials, additional to response time, online conference judgments have also been studied. A response time is a sum of the time required by a cognitive process to finalize a decision and the non-decision processes, such as motor movement. Confidence judgment is a report of one's confidence state in a subjective success likelihood of the decision choice and has been utilized to empirically evaluate slow decision tasks such as reasoning. To describe and evaluate fast decision cognitive processes, random walk models have been utilized since several decades. However, only a few studies have evaluated slow response times using the random walk process models. A random walk model is a process model that, given a state space and time, describes the probability of transitioning from an initial state to a final state. The state space in random walk model can also be used to describe a confidence state space. This helps to model decision tasks that records final confidence judgments along with response choice accuracy and time. For each response choice, the confidence state space can either be chosen arbitrarily or based on the confidence judgment scale administered in the decision trial. Two examples of random walk model over confidence state space are diffusion model and quantum model. It is important to note here that both diffusion and quantum model can define their state space in any manner suitable for the research and does not require to be confidence states. Diffusion and quantum random walk model can be described in terms of discrete or continuous state and time. Today we will discuss discrete state continuous time random walk model. In discrete state diffusion random walk model, the transition probability function utilizes an S by S matrix describing the likelihood of transitioning from current state to the neighboring state. The transition probability function in diffusion random walk obeys the law of total probability. Hence, at any given time point, the diffusion random walk can only be in one particular state. This video shows the evolution of a standard random walk model with drift. In the video, the y-axis represents the state space and the x-axis represents number of time steps. The number of steps is utilized to model the response time. Here, drift rate parameter is used to calculate probability of transitioning from current state to the next state. The starting bias parameter represents a participant's initial bias towards a response choice, and the decision threshold parameter represents the final state that should be reached to elicit the response corresponding to the border reached. Quantum random walk model assumes that a random walk exists in a superposition over all states at any time point. To describe such a transition mechanism, the transition probability function utilizes an S by S probability amplitude matrix comprising of complex numbers. Instead of obeying the law of total probability, a quantum transition model should obey the law of double stochasticity. To get probability distribution over state, the squared length of probability amplitude can be calculated. Quantum random walk model can also be described using drift rate, diffusion rate, and initial bias parameters. This plot shows how the probability amplitude evolves over confidence state, space, and time. Here, 7 confidence states minus 3 to plus 3 are used to describe random walk state space. Also here, minus 3 state describes high confidence towards incorrect response, and plus 3 describes high confidence towards correct response. The x-axis shown here is time, y-axis is the real part, and the z-axis is the imaginary part of the complex probability amplitude matrix. Take a note of the wave-like evolution pattern. Here, the drift rate and diffusion rate were fixed to 1. This plot shows the evolution of probability distribution calculated by taking square of the length of probability amplitude over confidence states. This probability distribution can then be further utilized to model response choice accuracy, time, and confidence judgments. Now we will see how one of our previous studies in one of our previous studies, we utilized diffusion random walk to simulate a reasoning process. In one of our previous studies, we have shown that manipulating the drift rate parameter within a trial can simulate within trial variations in empirically observed evolution of a reasoning process. In the plots shown here, the x-axis is the time step and the y-axis is the confidence state. The lines depict evolution of random walk model and the density plots depict the resulting response times distribution. We kept the drift rate constant in single stage scenarios with a low and high value signifying low and high ability to collect evidence towards a response choice. Then, in multi-stage scenario, we manipulated the drift rate within a trial using two non-linear functions over current state that approximated two patterns of confidence judgment evolution. These simulated response times are utilized in present study to evaluate goodness of model fit of quantum random walk model. A goodness of model fit study evaluates the effectiveness of chosen parameter estimation methods and model evolution methods given current model and observed data. A parameter estimated method is an algorithm that finds the best parameter value or fits a model to the given data. A model evaluation method examines the fitted model's effectiveness in describing the observed data. Although Bayesian inference methods of parameter estimation and model evaluation has been widely used to examine goodness of model fit of decision process models, these methods have not been widely used for discrete state continuous time random walk models over confidence state space. In the present study, we fitted the quantum random walk model proposed by Buzzmeier et al. In 2006 on the reasoning response time data simulated by a previous study. 50, 100 and 200 participants' response choice accuracy and time over 20 items was generated using the diffusion random walk model proposed in our previous study. This response dataset will be referred to as data generating process dataset for the remaining of the presentation. Present study utilized the shown likelihood function of quantum random walk model. In interest of time, we will only do a brief discussion about the likelihood function. This function is discussed in depth in Buzzmeier et al. 2006 paper Appendix C and Buzzmeier et al. 2012 book section 8.3.4.2. First, based on the initial starting probability amplitude psi 0, psi t is calculated to get the probability amplitude distribution at time t. Here u is the transition probability amplitude and is created based on drift rate, diffusion rate and response time unit tau. Then using M measurement matrix specific to a decision boundary, the elements of psi t vector are selected. Then squared length of psi t vector is calculated to get the probability or likelihood of being at a particular boundary. From the starting time point till response time steps -1, the no response matrix Mn is utilized to select the elements that are between the decision boundaries. In present study, -3 to +3 confidence states were used. States 2 and 3 described correct response boundaries, and state -2 and -3 described incorrect response boundaries. Non-centralized parameterization was used to describe drift rate parameter for each participant. Also, square root of Dirichlet distribution was used to describe the initial probability amplitude distribution over confidence states. The diffusion rate was kept constant and set to 1. Response dataset was divided into batches of 25 participants to reduce computational requirements. For each batch of 25 participants and 20 items, no U-turn sampling method was used to sample posterior distribution. 2700 posterior samples were generated in each of 4 sampling chains. Model convergence was evaluated using Gelman-Rubin R-hat metric. An R-hat metric utilizes the variance between and within sampling chains to identify whether chains are converging to a stationary distribution. The expected or ideal value of R-hat metric is close to 1. To examine the model fit, we utilize posterior predictive model check method. Posterior predictive distribution is the probability density function of unobserved data x hat given the observed data x and the posterior distribution of model parameters theta. In other words, we wanted to check whether the observed data X looks plausible given the fitted model. A posterior predictive check examines closeness of the posterior predictive distribution with observed data distribution by comparing, say, mean statistics or shape of the distribution. For each parameter posterior sample, one response time dataset of the same size as DGP or observed response time dataset was generated using weighted sampling with replacement method, which goes as: for each parameter posterior sample, first likelihood of individual DGP response time was calculated using the quantum random walk likelihood function. Using these likelihood values as weights, response times were sampled with replacement. Then the distribution of DGP response times were compared with the set of posterior predictive response time distributions. Pyro were used to specify the quantum random walk model and perform Bayesian inference. An R-hat metric close to 1 suggests that the model has converged. Each point in this plot shows R-hat value of an individual participant. As we can see here, the R-hat matrix remains close to 1 for majority of the participants. However, as the sample size increases, the value of R-hat also increases, suggesting that as sample size increases, no U-turn sampling algorithm struggles to converge. This plot compares the DGP or observed response times, shown in black, and posterior predictive response times, shown in blue. As we can see, posterior predictive response times closely fits the single-stage fast response times. However, as response time increases in the single-stage, slow, and multi-stage scenarios, the model struggles to fit the observed mean and shape of the response time distribution. This plot compares the mean of DGP or observed and posterior predictive response times for 50, 100, and 200 participants. As seen earlier, quantum random walk models struggle to fit larger mean response times. Present study found that as response time and within trial variability increased, the goodness of model fit reduced. Also, as sample size increased from 50 to 100 to 200, model converges and goodness of model fit reduced. Hence, although the quantum random walk model converged for smaller sample sizes, the model was found not effective in explaining the response times generated by assumed DGP of reasoning trials. Only 7 confidence states were used due to memory requirements of the model. The sampling process took 3.5 hours for a batch of 25 participants. This long execution time may not be desired in practice. The model compilation and execution time was found to be directly proportional to the number of participants because transition matrix is estimated for each participant, and response time, given the n-1 factor in the likelihood function, grows as the response time increases. Python JAX provides several methods to parallelize calculation over CPU cores, such as scan function. Such functions can be further explored to reduce the compilation and execution time. Also, a higher number of confidence states may help to better fit the slower response times. I would like to acknowledge Dr. Richard Golden and Dr. Stacy Warren for the continuous guidance and support during this study, and for providing the computational resources required to run these simulations. Thank you for your attention and have a great day.